Hi students, good morning everybody. In today's video we are going to see about the fourth unit electromagnetic induction and alternating current. Let us see in the introduction, in the previous chapter, that is in the third chapter, we learned that an electric current flowing through a conductor produces a magnetic field. This was discovered by Oersted. Later, Ampere proved that when a current carrying conductor behaves like a magnetic pole or dipole, these are the magnetic effects produced by the electric current. Physics then began to think the converse effect. That is it possible to produce a magnetic electric current with the help of the magnetic field? Using these concepts, many number of scientists did a many number of experiments and they established that the converse effect is also possible. Scientists by name Michael Faraday of UK and Joseph Henry of USA did simultaneously and independently a large number of experiments, and after their experiments they successfully proved that the conversion of magnetic field into electric current is possible, and this was later on established as the topic electromagnetic induction. Michael Faraday is credited with the discovery of electromagnetic induction. What is electromagnetic induction? The phenomena of converting a change in the magnetic field into electric current is called electromagnetic induction. In this chapter we are going to see some important concepts regarding electromagnetic induction. First of all, we will learn about magnetic flux. Magnetic flux IB is a term similar to electric flux. What do you mean by a magnetic flux? Magnetic flux IB through an area in a magnetic field is defined as the number of magnetic field lines passing through the area normally. And magnetic flux is given by the relation IB is equal to integration taken over a closed area B vector dot dA vector, where the integral is taken over the area and theta is the angle between the direction of the magnetic field and the outward normal to the area. In this diagram you can able to see a closed area, and this closed area is placed in a uniform magnetic field. N represents the outward normal drawn to the area. The outward normal is making an angle theta B with the magnetic field. So if the magnetic field is uniform over the area and is perpendicular to the area as shown in the diagram, that is the second diagram, then the above equation will become psi b is equal to integration of b vector the dA vector is equal to BA cos theta. Here theta becomes 0, cos 0 becomes 1, so the above equation psi b becomes BA. The SI unit of magnetic flux is Tesla meter square. It is also measured in Weber, and 1 Weber is equal to 1 Tesla meter square. Fleming's right hand rule. When a conductor moves in a magnetic field, it will induce a EMF in the coil in the conductor, and as a result a current is produced. When a conductor moves in a magnetic field, the direction of motion of the conductor, the field and the induced current are given by Fleming's right hand rule. If you take your right hand and stretch the forefinger, the middle finger and the thumb of your right hand such that they are mutually perpendicular to each other, then according to Fleming's right hand rule, the forefinger represents the direction of the magnetic field, the thumb represents the direction of the motion of the conductor, and the middle finger represents the direction of the induced current. It is stated as follows: the thumb, the index finger and the middle finger of right hand are stretched out in mutually perpendicular directions as shown in the diagram. If the index finger points the direction of the magnetic field and the thumb indicates the direction of the motion of the conductor, then the middle finger will indicate the direction of the induced current. Fleming's right hand rule is also known as generator rule because it gives the direction of the induced current in a generator, which is used to produce an alternating current. Next, motional EMF from Lorentz force. Consider a uniform magnetic field in this diagram indicated by the crosses. In this magnetic field, a rod AB is placed perpendicularly to the magnetic field. Let L represents the length of the rod. You all know that the conducting rod contains a large number of free electrons. The rod AB of length placed perpendicularly to the uniform magnetic field moves from left to right with the velocity of v, with a constant velocity v. When the rod moves, the free electrons present in the rod will also move with the same velocity v in magnetic field. As a result, a Lorentz force will act on the free electrons in the direction from B to A, and it is given by the relation FB vector is equal to minus E into V vector cross B vector. This action of the Lorentz force will accumulate the free electrons at the end A of the rod. The accumulation of free electrons will produce a potential difference across the rod, which in turn establishes an electric field in the rod along the direction BA. Due to the electric field, the Coulomb's force starts acting on the free electrons along AB, and it is given by Fe is equal to minus EE. The magnitude of the electric field E keeps on increasing as long as accumulation of electrons at the end A continues. The force E also increases until equilibrium is reached. When the equilibrium is reached, the magnetic force Fb and the Coulomb force balance each other, and no further accumulation of free electrons at the end A takes place. So magnitude of Fb is equal to magnitude of Fe under the equilibrium condition. So magnitude of minus E into V vector cross B vector is equal to minus EE. Here minus E into V vector cross B vector represents a magnetic Lorentz force, and minus EE represents the electric force experienced by the electrons. Since theta is equal to 90 degrees, since V and B are perpendicular to each other, theta is 90. So when theta is 90, VB sin 90 is equal to E. So VB is equal to E. The potential difference between the two ends of the rod, V is equal to EL. Substitute E is equal to VB from this equation. In this equation, you will get the potential difference across the ends of the rod. V is equal to VBL. Here V small v represents the velocity and capital V represents the potential difference. Thus the Lorentz force on the free electrons is responsible to maintain this potential difference, and hence produces an EMF. E is equal to BLV. As this EMF is produced due to the movement of the rod, it is often called as a motional EMF. If the end A and B of the rod are connected by an external circuit of total resistance R, then the current I is equal to E by R, which is equal to BLV by R, flows through it. The direction of the current is found by Fleming's right hand thumb rule. Self-induction. What is an inductor? Inductor is a device used to store energy in a magnetic field when electric current flows through it. The typical examples of inductors are a coil, a toroid, and a solenoid, as shown in the figure. Inductance is the property of inductors to generate an EMF due to the change in the current flowing through the circuit, either in the inductor itself, self-induction, or to change a magnetic field due to the change in the current in the neighboring circuit, which it is magnetically linked. We will now study about self-induction and mutual induction. Self-induction. What do you mean by a self-induction? When electric current flows through a coil, will set up a magnetic field, and because of the change in the magnetic field, an EMF is induced in the same coil itself. Then that phenomena is called as a self-induction. An electric current flowing through a coil will set up a magnetic field around it. Therefore, the magnetic flux of the magnetic field is linked with the coil itself. If the current passing through the coil changes, then the magnetic field lines around the coil will change, and so the magnetic field will change. As a result of the magnetic field linked with the coil changes, an EMF is induced in the same coil. Such a phenomena is called self-induction. This diagram helps us to explain the self-induction. This is a coil, it is connected to a battery, and this is a rheostat. By adjusting the rheostat, the current passing through the coil can be changed. When the current through the coil changes, as given in the diagram, a magnetic field will be present around the coil shown by the magnetic field lines. And when the current passing through the coil is changed, the magnetic field around this coil will also change. As this coil is placed inside a magnetic field, changing magnetic field, it is clear that a self-induced EMF will be induced in the coil. And now let us see some important facts about this. Let psi b be the magnetic flux linked with each turn of the coil. Let there are n number of turns in the coil, then the total flux linked with the coil is n psi b, which is called as flux linkage, and the flux linkage associated with the coil is proportional to the current I passing through the coil. N psi b is proportional to I, or N psi b is equal to Li. What is L? L represents the constant of proportionality, which is called as a self-inductance or coefficient of self-induction of the coil. So L is equal to N psi b by I. In this equation, if you put I is equal to 1 ampere and then L becomes N psi b. So self-inductance, or simply inductance or coefficient of self-induction of a coil, is defined as the flux linkage with that coil when 1 ampere of current flows through the coil. When the current I changes with the time, an EMF is induced in it, and from Faraday's law of electromagnetic induction, the induced EMF E is equal to rate of change of magnetic flux. So E is equal to minus N psi b by dt. Instead of N psi b, you substitute Li in this equation, you will get E is equal to minus d by dt of Li. Here L is a constant, so we can take it out of the integration. When L is taken out of integration, induced EMF E is equal to minus L into di by dt. So L is equal to minus E by di by dt. The negative sign indicates that the self-induced EMF always opposes the change in the current with respect to time. In this equation, if di by dt, that is the rate of change of current, is 1 ampere per second, and then L becomes minus E. That means L is equal to opposing self-induced EMF. So inductance of a coil is also defined as the opposing induced EMF in the coil when the rate of change of current through the coil is 1 ampere per second. Unit of inductance. Inductance is a scalar quantity, and its unit is Weber per ampere, or VSA minus 1. It is also measured in Henry. 1 Henry is equal to 1 Weber per ampere, or 1 VSA minus 1. The dimensional formula for self-inductance is ML square T minus 2 A minus 2. If I is equal to 1 ampere, N psi B is equal to 1 Weber turns, then L is equal to 1 Henry. Therefore, the inductance of the coil is said to be 1 Henry if a current of 1 ampere produces unit flux linkage in the coil. If di by dt is equal to 1 ampere per second, and if E is equal to minus 1 volt, then L is equal to 1 Henry. Therefore, inductance of a coil is 1 Henry if a current changing at the rate of 1 ampere per second induces an opposing EMF of 1 volt in it. Let us now see the physical significance of inductance. We have already learnt in 11th standard in mechanics, in translational motion, mass is a measure of linear inertia, and in rotational motion, moment of inertia is a measure of rotational inertia. Generally, inertia means a position to change the state of change its state. Now, in electricity, just like inertia in mechanics, both in translational motion and rotational motion, inductance plays the same role as mass and moment of inertia. That is, it is given here. The inductance plays the same role in circuit as mass and moment of inertia play in mechanical motion. When a circuit is switched on, the increasing current induces an EMF which opposes the growth of the current as given in the diagram. In the second diagram, when a circuit is broken, that is when the current starts decreasing and inducing EMF opposes decreasing current in the reverse direction. Thus, inductance of the coil opposes any change in current and always tries to maintain the current to the same state, original state. So, in mechanics, mass plays a role of inertia, playing the role of inertia. In rotational motion, moment of inertia is playing the role of inertia, and in electrical circuits, inductance plays a very important role. Now let us see the derivation for self-inductance of a long solenoid. Consider a long solenoid of length L and cross-sectional area A. Let small n be the number of turns per unit length, which is also called as a turn density. An electric current I is passed through the solenoid. What will happen? A magnetic field will be produced inside and outside the solenoid, but the magnetic field produced inside the solenoid is uniform. This diagram represents a long solenoid of n turns and having a length L. When the current passes through the solenoid, a uniform magnetic field will be produced inside the solenoid along the axis of the solenoid. The magnetic field at any point inside the solenoid, as we have already seen in the third chapter, is given by B is equal to mu naught Ni, where mu naught represents the permeability of free space or vacuum. As this magnetic field passes through the solenoid, the windings of the solenoid are linked by the field lines. So the magnetic flux passing through each turn of the solenoid is given by psi B is equal to integration taken over a closed A area B vector dot dA vector, which is equal to BA cos theta. Here theta is equal to 0 degrees. So psi B is equal to BA, where psi B represents the magnetic flux linked with each turn of the solenoid. Substituting B is equal to mu naught Ni in this equation, psi B is equal to mu naught Nia. The total flux linked with the solenoid for all the n turns is given as n psi B is equal to NL into mu naught Ni into A. So n psi B, which is the flux linkage with the solenoid or the total flux linked with the solenoid, n psi B is equal to mu naught n square Al into I. We all know that n psi B is equal to Li. Now equate Li and mu naught n square Al into I. We will get we will get a equation. The equation is L is equal to mu naught n square Ai. From the above equation, it is clear that self-inductance depends only upon the geometry of the solenoid. That is, L depends only upon the number of turns per unit length, area of the coil and length of the coil, and also the medium present inside the solenoid. If the solenoid is filled with the dielectric medium of relative permeability mu r, then L is equal to mu n square square AL, or L is equal to mu naught mu r n square AL. This is the expression for the self-inductance of a solenoid. We already know that when inside a solenoid or a coil which is used as an inductor, energy is stored. The energy stored in the inductor is magnetic potential energy. Now we are going to see an expression for energy stored in an inductor. Whenever a current is established in a circuit, you all know that the inductance opposes the growth of the current. Now, in order to establish a current in the circuit, some work will be done against the opposition by some external agency. The work done by an external agency in order to establish a current in the coil is stored as magnetic potential energy. Let us assume that the electrical resistance of the inductor is negligible and the inductance alone plays a part here, and the inductor alone is considered. The induced EMF in the inductor at any instant of time is given by E is equal to minus L into di by dt. We have already studied this, is it not? dW be the work done in moving a charge dq in a time dt against this opposition. Then dW is equal to minus E into dq. Because dq is equal to I into dt, I can write dW, the small amount of work done in establishing a small current di through this inductor, is equal to minus EI dt. Substituting E from this equation, in this equation we will get dW is equal to minus of minus L into di by dt into I dt. dt cancels, so dW is equal to Li di. Therefore, the total work done in establishing a current in the coil W is equal to integration of dW, which is equal to integration of Li di from 0 to I. On integrating, we will get L into L square by 2 from 0 to I. So, W is equal to half Li square. This work done is stored as magnetic potential energy. UB is equal to half Li square. The energy density is the energy stored per unit volume of space, and it is given by UB, small ub. Capital UB represents the total energy stored and small ub represents the energy density, that is energy per unit volume. Small ub is equal to total energy divided by volume, which is equal to UB by AL, where A represents the area of the coil and L represents the length of the solenoid. Volume of the solenoid is AL. So, UB is equal to, instead of capital UB, substitute half Li square. You will get UB is equal to Li square by 2 into AL. Instead of L, you substitute mu naught n square AL. So, UB is equal to mu naught n square AL into I square by 2 AL. AL gets cancelled, LL gets cancelled, and finally you will get UB is equal to mu naught n square I square by 2, and UB is equal to B square by 2 mu naught, because B is equal to mu naught Ni. So, this is the expression for energy density, and this is the expression for the total magnetic potential energy stored in the inductor. Thank you.